John, I believe you had a question?
Yes, on the left is the second question, and it says the formula for the slope of each graph in terms of the speed of sound, but I don't know how that relates to the speed of sound. Cause I just got a meters per second slope.
Alright, so, first harmonic, this is the water tube.
Yep.
Alright, so first harmonic right here, you've got, this is where the water is, and then you've got the open end where it's the loudest, because you have the biggest vibrations here. So, how many wavelengths is this?
It's half, halfway.
4.
A fourth.
Yeah, it's a fourth. Or a full wave looks like that, and this is going from a node to an antinode, so it's only a quarter of the way. Alright, so whatever that distance is right there, that length is a quarter of a wavelength.
Okay.
So the wavelength is 4 times that length. I know that the speed that the wave is traveling is equal to, wait, what was the wording again?
It says, what are the formula for the slope in terms of the speed of sound, and what is the speed, the formula for the speed of
Okay.
sound in terms of slope?
You plotted, it was something versus period.
Period.
It was,
Harmonics, first harmonics versus period.
yeah, and, the next one was
Was
the
third
one.
harmonics versus period.
So it was length, right?
Mhm.
The first harmonic
Yeah.
versus period. Alright, so we need to somehow relate those two. I know that the period is 1 over the frequency. The speed is wavelength over period, or wavelength times frequency, whichever one's more convenient. Probably this one. And the wavelength, so we have the speed of sound,
Mhm.
is equal to the wavelength times over the period, and I know the wavelength is 4L, so that's 4L over the period. So depending on how you want to do this, did I use V for the speed, or did I use C?
Used, the,
V, okay. So this is the relationship we're looking at here. And if I put it into y equals slope x plus b form, where this is x, and this is y. Slope is whatever we're multiplying times, well, period. So, since L is my y value, I'm gonna solve for L there, so L is equal to VT divided by 4, or V over 4 times T, plus 0 to get to the full form. So therefore, what is the formula for the slope?
it would be V over 4?
Yeah. And the formula
For the first one.
for the first harmonic.
Yeah.
Then that'd be 2/3 to that for the third harmonics.
Third harmonic would not
B.
be 2/3, because third harmonic,
Wouldn't it be 3/4?
this would be 3/4,
Yeah,
so that would be 4/3,
For third
which would
harmonic.
then flip, so it would end up being 3/4 here.
Yeah, 3/4.
Okay. And, also my graph, I got the R squared value of 1 for my graph.
So it lined up perfectly?
Oh, yeah, well, it rounded up to 1.
How many, did you?
It was,
take-
the third decimal. So it was 999, and then whatever,
And then something else for the fourth
Yeah.
one? Something bigger than 5 or bigger
Yeah.
for the fourth one? Okay,
but you can see that it's not exactly perfect on the graph.
okay. And typically, take it out to however far you need to take it out, so that I'm not seeing 1 there, but,
But I don't know how to change that, so
Ah.
it doesn't round.
okay. Typically, if you click on it, if you click on the formula, the whole thing is gonna basically be highlighted, then you can go to format, and then add however many decimal places you want. in some version of Excel can do it, it's just a matter of which version of Excel you have and how did they change it, just to mess with people's heads.
I have Google Sheets that I use.
Okay.
I don't know if I can change.
I've not worked with Google Sheets as much for graphing. All right, other questions at the moment? All right, you've told me and I'll look out for it.
Okay. Yeah, it's not letting me edit the Oxford document.
Yeah, I probably should mess with Google Sheets a little bit more so it can help with things like that. Other questions? As a reminder, you've got the quiz on 22 on Thursday, Master's Set on 22 through Thursday, and the test a week from today. All right. You about to write something, just so it's down? Pause. I'm going to skip chapter 33 for right now. I'm going to hit 33 tomorrow. In essence, my notes are done. That's the problem there. I could get most of it, but I want something a little bit more coherent. So we're going to do 34 now. And then 33 tomorrow. So one of the things I'll mention tomorrow.
You say you're skipping 33?
I'm skipping 33 today, I'm gonna come back and do 33 tomorrow.
We already started on it, so.
Yeah,
Okay.
just the very basics of it. The 33, the tough part of 33 is some of the language that they're using there, so, at least for the way my mind works. So I'm gonna hold off and try to do something more coherent tomorrow. But one of the properties, one of the things I will mention tomorrow is that one of the properties of light is the fact that it reflects. And so chapter 34 deals with the reflection piece of it. And that if I have a surface and light coming in, so I have some surface here, light comes in, it's gonna bounce off. Now typically when you're talking about the angle of incidence, the angle at which it hits, talk about the angle from the vertical. So from sort of an imaginary line that is perpendicular to the surface that's being hit. And so if light is coming in this way, this would be the angle of incidence. That's supposed to be an arrow there. And then it bounces off with the angle of reflection. So theta I, angle of incidence. Theta R, angle of reflection. And so one of those nice little principles is the fact that the angle of incidence should equal the angle of reflection. It doesn't always necessarily seem that way, but it happens. So if I took a mirror, and I have a mirror here, and I shine the light onto it, the light, I think we can pretty well come up pretty darn close that this holds true. And one of the labs that we'll do this week involves that. But, and I should say flat mirror, or plane mirror, plane P-L-A-N-E, as opposed to A-I-N. Flat or plane mirror. But it doesn't always necessarily look that way. and the fact that if we go down on a microscopic level, no surface is perfectly smooth. The mirror is probably going to be the best that we can afford here. But if it's something like this, as the light comes in, it's still, this principle still holds true, but we don't necessarily see it because if it's not flat, that's gonna hit and that's gonna bounce down here, which is then gonna bounce like there, and it's gonna be shooting off at that angle. It still holds true that the angle incidence equals angle reflection, but on the macroscopic level, it doesn't necessarily look that way. However, we are going to assume some nice ideal situations here so that we can model this quite nicely. So we're going to start out with the concave mirror. So we're going to assume that perfect angle of incidence equals angle of reflection. And we're also going to assume, okay, so not flat or plane. But we'll pretend for the math. And you'll see what I mean by that piece at the end, and we're not. Yep. So if I have a mirror that looks like this, this is the center of the mirror. And if I think about a tangent line right there at that surface right there, and draw a line perpendicular to it, and then I take the tangent line right there, and if I take a tangent line anywhere, and draw a line perpendicular to it, they should hit some at the same place here, and this would be known as the center of curvature. Curvature, yeah, spell it right, just not necessarily legibly. And the distance from the mirror to this point is the radius of curvature. The distance from here, and we can go for some visual effects here. Ooh. Radius of curvature. So let's go through and derive a formula that we will use again and again, even though we're going to derive it several times, or at least twice. Now the book starts with just the plane mirror. I think deriving this formula first and then showing how it applies to the plane mirror works better. So I'm going, the sections of chapter 34 slightly out of the book's order. So this is what I mean by pretend that it's flat from a math point of view. So I'm going to pretend I have a mirror that the radius of curvature is really not too bad. It kind of looks as somewhat flat here, with a radius of curvature here. So the distance from this point to this point is r. And I have an object here. The distance from the center of the mirror to my object, we're going to label P. And the height of this we will label as y, sub O for object. And so this point right here, if I think about this as, if this is the origin right here, this point right here would be the point P and y0. So you can sort of think about it like a coordinate system, like this is the x-axis and that's the y-axis. So if the top of this image here is giving off light, well, light's going to go off in every direction, but we don't need to know every direction. All I need to do is figure out where is the image going to be. So light that goes through my center, the center of curvature, will hit the mirror and then bounce right back.
It would bounce right back at an angle.
Because the mirror, in reality, it is curved, even though it treated it like it's flat in
Oh,
terms
okay.
of the map, but it is curved. So this distance right here is P minus R. Another ray of light that's coming in or that's being emitted is going to hit smack dead into the center here. And let's see if we can actually get a different color here. That is not significantly different. When it hits the mirror, it hits the middle of the mirror here, that's the point where the tangent line actually is flat, and so it should just bounce back. Might get the same angle. So this angle and this angle are the same. Just like for the purple, or whatever color this is, this angle and this angle are the same. And those two rays meet, so I got the light coming off of it, the two rays are going to meet at this point right here. And so that's where the head of the image is. And the distance from the mirror, from the center of the mirror to this, to where the image is, this distance here is labeled Q. And this is the point, well, I go Q out, and then I go down, and then I go to the point Y sub I. I for image. Over object, I for image. Recognize in this particular scenario, Y sub I is a negative number. So in this scenario, then we emphasize that. In this scenario, Y sub I is negative. All right, so now we're going to do a little geometry here, a little bit of trig, more geometry than trig. All right, so if I think about this angle right here, which I'm going to label as theta 2. I have the tangent of theta 2, and for a right triangle here, it's a right triangle trig. What is tangent?
Opposite over adjacent.
Yep. So if I'm looking at this top right triangle here, my opposite side is y sub 0. My adjacent side is this one right here, which is just p. If I look at the smaller triangle, which has theta sub 2 in it, my opposite side is negative yi divided by q. Manipulating just a little bit here. I have the size of the, let's see, I'll do image. So yi is the height of the image, a negative number. And I want yi here instead of negative yi for a reason. Over yo. So basically bring yo down, means I'm bringing q up. And so that's q, negative q over p. And this is known as the magnification. Magnification could be positive or negative. A negative magnification means that the object of the image, one is inverted form of the other.
Is that Q over P?
That's Q over P. Because I have two fractions equal to each other, so I move stuff across the diagonal, so I basically moved y sub O down and Q up. Questions up to here?
That is a negative Q,
It's
correct?
the negative there. I guess, and then I guess I brought the negative over. I have a negative here, and so a negative has to show up somewhere, so I can have it on the right side.
Is that equal or negative in front of?
Alright. So, the distance from the axis to the head of the image, so basically the height of the image over the height of the object is equal to negative, that's equals, negative Q divided by P, which is equal to the magnification. Hopefully more readable. All right, any other questions at this point?
So in reality, you could say negative yi over p. You can transpose, because the y and q are equal, right?
The y and q are not equal, the
The ratio,
ratios are equal,
okay.
and so there's a negative in there. We'll apply this to an actual problem, and we've got the formula.
So Q is the intercept of the two.
Q is the distance from basically the mirror, the center of the mirror, to where the intercept is. It's the horizontal distance.
So if you have one of the angle, if you have one of the angles, figures, it should be same as the other angle. But
Right.
theta and both of them are the same,
Those angles are indeed the same.
okay.
Based on this idea that the angle of incidence, the angle in which the light comes in,